Welcome to this tutorial on topological sort using depth-first search. This is a fundamental concept in graph theory and computer science, often appearing in coding interviews and real-world scheduling problems. Today, we will explore how to order tasks based on their dependencies using a simple yet powerful algorithm. First, let's define what we are trying to achieve. Topological sorting provides a linear ordering of vertices in a directed graph. The rule is strict but simple. For every directed edge from vertex U to vertex V, vertex U must appear before vertex V in the ordering. Think of it as organizing a list where a parent always comes before its child. To understand this intuitively, think about university course prerequisites. You cannot take Calculus 2 before you pass Calculus 1. Calculus 1 is a dependency for Calculus 2. Topological sort is simply the algorithm that takes all these courses and their prerequisites and arranges them in a single list that you can follow from start to finish without breaking any rules. There is one crucial condition for this to work. The graph must be a Directed Acyclic Graph, or DAG for short. This means there cannot be any cycles. If task A depends on task B and task B depends on task A, you are stuck in a loop. You can never start either task. Therefore, topological sort is impossible if a cycle exists. Now, let's look at how we solve this using depth-first search. The strategy relies on two main concepts. First, we use DFS to traverse as deep as possible into the graph. Second, we use a stack to record our completion order. Specifically, we only add a node to our stack once we have finished visiting all of its children. Why do we use a stack? Consider a parent node U and its child V in a depth-first search. We visit U, then immediately go to V. We will finish processing V before we finish processing U by adding a node to the stack only when it is completely finished. The child V gets pushed first, and the parent U gets pushed afterwards. When we pop from the stack later, U comes out before V, which is exactly the order we want. Let's walk through an example. Here we have a small graph. We start our DFS traversal from node 0, which goes to 1, then 2. Let's say we are currently at node 2. We must visit all its neighbors, nodes 3 and 4, before we can mark node 2 as done. DFS continues. We visit node 4, it has no children, so it finishes. We push 4 to the stack. Then we visit node 3, it finishes, and we push 3 to the stack. Finally, now that all children of node 2 are done, node 2 itself is finished. We push 2 to the stack. Notice how the dependencies are at the bottom and the dependents are piling on top. We continue this process until the entire graph is visited. Once the recursion unwinds completely, we have a stack full of nodes. To get our final topological sort, we simply pop everything off the stack. The result is a valid linear ordering where every dependency requirement is met. Here is the pseudocode implementation. We have a standard DFS function. We check if a node is visited to avoid reprocessing. We loop through all neighbors recursively. The magic line is at the end, stack.pushNode. This happens only after the recursive calls return. We also need a main loop to ensure we cover disconnected parts of the graph. This algorithm is highly efficient. The time complexity is big O of V plus E, where V is the number of vertices and E is the number of edges. This is because we process each node and each edge exactly once. The space complexity is big O of V, required for our visited array, the stack, and the recursion depth. To wrap up, remember that topological sort orders tasks based on dependencies and only works on directed acyclic graphs. The DFS approach is elegant. Simply push a node to a stack only after its children are visited. Finally, pop the stack to get your result. Thank you for watching.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.